Well, okay. Hopefully I can do something. There's a homework due on Wednesday, correct? Right. Okay. And we did part of, yeah. 11. And we have midterm 3 the following, actually 1 week from today, right? And the final exam is on December 11th. Homework 11 or homework 12? 11. I don't know why it's written homework 12. Okay. Okay, yeah, our goal was to somehow find a derivation for the method of images that we have that we introduced before, and for that we said it might be good to do Fourier transform. So that we go back a little. So this is a differential equation for method of images. So differential equation for method of images. or we can also say differential equation when conductors are involved. We already said that the differential equation we have is equal to, so this is the rho where E is equal to epsilon times electric field. Correct. And we also have cross E is equal to 0. So our differential equation. Put this together. First is curl being 0 tells us that electric field is equal to negative gradient of the potential. It's like saying force is equal to the negative gradient of energy. Electric field is negative gradient of electric potential. Put this in here. Our equation is, so this is called a Poisson. Right? This is Poisson equation, right? So basically, if I substitute this into this, with D is nothing but epsilon r times gradient phi. And it's a vector differential equation. It's a relatively hard equation to solve. And we were working with planar geometry. So what we did was last time, we Fourier transformed this whole quantity. So the specific problem we are interested in is that epsilon of r is equal to only z dependence is there. So there is no x and y dependence. And in particular, it's much simpler for a specific case we are interested in is this is infinity for z less than 0, and it's equal to vacuum for z greater than 0. So that's the material we are interested in. So if you were to plot this, so this is conductor, right? And a conductor means as far as electric field goes, there's nothing existing there. So this is pretty much, we said epsilon has to be infinity because electric field has to be 0. And on this side, this is vacuum. But we want to keep a positive charge here. We want to place a positive charge right in front. So that's the material. We also want to say that rho of r is equal to q times, when you're on for z greater than 0, there is 1 point charge. So that's delta of x times delta of y times delta of z, a little front of this, so this is z minus a. Slightly to that. So that's a material, that's your chart. So that's what we would like to do. For this problem, we started by saying, let's Fourier transform this. Everything is in the z direction. So we said the other two coordinates, we simply said we'll Fourier transform it. This is x, y, z, x and y in the plane. So we wanted to Fourier transform this instead of looking for this whole electric potential. We said we will look for the modes of the Fourier modes associated with this potential. E raised to I k per r per. So our purpose X and Y notice, but instead of looking for this electric potential, you expand this as a Fourier transform, and you're interested in this quantity, K per of Z. Right, so basically, I don't want to talk about the other two pieces or the other two dependence in X and Y. Instead, we will talk about the Fourier mode. So this is the Fourier transform of this, or write this electric potential as an expansion, and this will be the Fourier modes. If you think of it as sine and cosine, these are the modes. Same thing can be done for the charge also. So it will be R per and Z is equal to 2K and this will be rho K per and Z. In fact, if for the particular situation, this is for any general charge, for the very particular situation, this will come out to be having no K dependence, and we'll show that in a few minutes. Okay, so what is, how do we proceed? We said we would like to, instead of looking for the differential equation for the electric potential, look for the differential equation for the Fourier modes, and everything in that will have only Z dependence, so it will be a one-dimensional differential equation instead of a three-dimensional differential equation. We already showed that the gradient, so this is what we did last time. So we said gradient of phi or per of Z is equal to this. So gradient, remember, will have two pieces, one associated with the gradient in the X and Y direction. This is integral d2k over 2 pi whole square times e raised to I k per with r per. So everything is happening in the Fourier transform. Instead of having d by dx plus d by dy plus d by dz, that's your gradient. Instead, it is simply plus I k per plus z hat times d by dz of phi of k per times z. So what is pretty much practically what has happened is that instead of talking about the gradient, the normal gradient, which is x hat d by dx plus y hat d by dy plus z hat d by dz, this inside the integral, it is, now we have to be inside because there is a k perp in it, cannot come out. This has, in the Fourier space, the derivatives have become just k algebraic. And that's typically the advantage you gain in the Fourier space. Instead of talking about derivative, we're just talking about a Fourier mode. The price is, that's not the complete solution. After I find the solution, I have to make do an integral to come back. Right? So I'm at this stage at this point. I'll be able to only get an equation for phi. Once I do that, I have to make that integral to completely come back to your. So let's see how this works. So if that's the case, what's my differential equation? We have only a z dependence in there. So gradient dotted with epsilon z times gradient. Right. So this whole operator, and let me introduce the negative sign also there. Right? That's phi of r perp comma z. I would like this whole thing. It seems like earlier there is an x dependence, y dependence, z dependence, but let's use this idea in here. Notice these operators can go through this integral, enter the integral, you k perp e raised to I k perp, and this can enter. So this is there's already a minus sign. And I k perp plus z hat d by dz epsilon z. Seems like a big complication here, but all this will simplify, and the final differential equation will be pretty straightforward. Phi of k perp so it's just doubling this. Already we showed that the gradient involves ik perp. The double of that will go through. It was crucial that this did not have any x and y dependence, because then otherwise this split wouldn't have happened. So that was crucial. This is perpendicular. There are cross terms. Ik perp dotted with z is 0 because ik perp is in the xy plane. So that's 0. So this simplifies a little. At least the vector nature goes away. R perp, and your differential equation is simply, let me write the z component first. So that is d by dz epsilon z. Notice our epsilon has a lot of simplicity too, right? It's either infinity or it's a constant, so it cannot come out. But as it is, let's keep it very general. And this is minus k perp square of epsilon z. So that's our left-hand side. Let's do the right-hand side also very quickly.
Exponential is so positive.
Exponential double again?
Isn't it positive?
Oh, plus, yes. I don't know why I switched. Yeah, thank you. Yeah, it should be plus. Yes. Anything else? Nothing? Okay, so notice we are now talking about a specific case when there is a point charge in front. So there is a simple, slight simplicity in here. Recall that your delta function can be represented in terms, so you can say what is a Fourier transform of a delta function. That's where its delta function has a very special Fourier transform. And what is it? What is the Fourier transform of delta function? It actually is just one. Okay, so think of it as, remember that if you have some x dependence in there, x times y, this is your x, and if there is a k dependence, it spreads out, right? So this is your k. So k times x, delta type k, x times delta k is approximately 1. So if the spread in x is really small, That means the spread in K has to be extremely large, and that is the oscillations that come. Very simplistically speaking, one more way of looking at it is this. Let's do this integral, right? If you were to do this integral at x equal to 0, it should give you an infinity, and otherwise it should be a 0. So let's put x equal to 0, right? So then this goes to 1, and that is minus infinity to plus infinity. What about x not equal to 0? If x is not equal to 0, this is minus infinity to plus infinity. These are oscillatory functions. That's not very immediate as whether that is 0 or not. But think of this as minus n to plus n, where n cycles come in, and then take the limit n tends to infinity. Right? If you have, so let's think of it as this one. So you're going in repeated cycles, right? So let's say this is lambda. Yeah, so let's say n times lambda. You go from minus n lambda to plus n lambda. This is cosine, and that is a sine, which will always be 0 if you go in cycles. Correct? So that gives you an argument that, yeah, this must be 0. Right? So that's a very hand-waving argument, but delta function has this representation. Is that roughly acceptable? Okay. No, it's not satisfying. let's try this. Okay.
I mean, I understand the principle. I just don't know. And it's almost like it's like you expect it to be 0, like it averages to 0, but you can't say. I would make the claim that you can't say if you go to infinity both sides of it.
That's correct. That's correct. So that much. Okay. So let's.
Yeah, I know that would be a divergence, so we can.
Extra credit, right? Check out. Okay. Extra credit. Okay. Try this. Okay. Try to show that. Remember, delta function. We have to always show that it is 0 when x is equal to 0. It should be equal to infinity when, it should be 0 when x is not equal to 0, it should be infinity. One more thing, remember, is the integral of this. Right? Integral of del J of x, that's very crucial. Infinity is there, but what about the integral of del J of x? Del J of x. What happens if you were to put this in? Okay. And you want to show that that's actually equal to 1. So check that out. I mean, just basically substitute this in there and see whether that actually goes to 1 or not. Is there an immediate way of seeing this? Since you bring it up. Yeah. It's an immediate. Yeah, let's proceed, and I'll come back to this. I'll try to give you an argument there, but this is I think let's proceed with this at this point. Okay, because I started late. Let me, yeah, so immediate. Yeah, looking. Okay. So the idea is, what I'm trying to propose is that the delta function has 1 as your Fourier transform. Okay. How else can I? Yeah. Another time. Okay. Which means that my Fourier transform for rho, which is q times delta of x times delta of y times delta of z minus a. If I were to write this simply in the Fourier space, so this leads to 1, that leads to 1, and it is simply integral d. Oh, so this is the Fourier transform I'm writing, so it is simply q times delta of z minus a, which is, when I write this, it will be inside of this integral. So this is also equal to integral q times d2k per over 2 pi square e raised to I k per dotted with r per times delta of z minus a. The advantage here is that there is no k per dependence on it. Okay, is that clear? So if I use this, okay. Did I just now move or already it was?
I think you,
Or maybe I was trying to go there before and the last part.
yeah, I think it was over there before.
Okay, so I think just for the recording, I think we just showed that the Fourier transform for this charge density for a point charge will be just delta z minus a. Okay, so overall, our differential equation becomes, so just rewrite it. This was our equation in the position space. Instead, in the Fourier space, this becomes negative k per e raised to ik per r. That's your Fourier expansion if you want. d by dz epsilon of z and minus, right? Minus k per square that's the Fourier mode. And on the right hand side, you have exactly the same integral. That's the whole point. We're trying to motivate. And this is q. So there's a q. Let me write it here. One way one can interpret your Fourier expansion is that these are eigenfunctions, right? These are like unit vectors. There's an expansion. These are the coefficients on the left, and these are the coefficients on the right. And since it is a complete set, Fourier expansion is a complete set of eigenfunctions. If you have an eigenfunction that's unique, on the left side should be exactly equal to the right side. It's like saying a vector A is equal to, let's say, I times x times j times y. If that is equal to 3 times I plus 2 times j on the right, then you say 3 is equal to x and y is equal to 2, right? These are components has to be the same. So just because a Fourier expansion on the left is exactly equal to the Fourier expansion on the right, that means the Fourier modes have to be the same. Again, why? Because it's a complete set of eigen functions. Fourier expansions is unique for a particular function. This implies, now this is where you get into the one-dimensional part. The modes can be taken away separately, and you get a differential equation in one dimension. Equal to Q times delta of Z minus A. So we solve for the Fourier modes using this differential equation. And remember, we shouldn't forget, let me recall that my main electric potential is in the position space. This is the Fourier space. So I have to do this integral to get my final answer. But we sacrifice that. We say that we understand Fourier space so well that we are good with the Fourier modes itself. So if we understand how these modes look like, we can do very well. So what is this differential equation for our scenario? So we go back here and ask how do we solve that differential equation, right? So this differential equation is first of all, that is for z equal to 0, z less than 0, it doesn't exist at all, right? So there is only z greater than 0. So for z equal to z less than 0, right, epsilon is infinity, so this doesn't exist, right? So no equation. It basically tells us that our electric field is 0, so phi is constant, whatever is on the boundary will be the same. So no equation. Phi of k perp of z will be equal to phi of k perp at z equal to 0, right? Because of continuity condition. So if I know the boundary, then I'll just say that everywhere it is the same, which we already said that it's a conductor, the grounded conductor, which will be 0. What about z greater than 0? Z greater than 0, this is just epsilon naught. So that's minus square by z square minus k perp square. Now there is still right, this is partial derivative. No hurts. Times phi of k perp z, that's equal to q over epsilon naught times delta of z minus a. Right. This is also called, like at this stage, if I were to remove this, this is called the Green's function. So if q over epsilon naught is equal to 1, this is called the Green's function equation. It's just a known feature, and let me relabel this z comma z prime. Right? So this is called a Green's function equation. If I know the answer for this, I immediately know that if I replace g with phi, I get the answer for it. So this is called the Green's function. But this equation is very straightforward to solve. Why is that? It seems like there is a delta function, but I use a property of a delta function. So here is my strategy that we do this on Monday, but the strategy is going to be g of z comma z prime is equal to 0. Already Z cannot be less than 0. If Z is greater than 0 and less than Z prime, where Z prime is A, right, wherever the charge sits. Z prime is A, but in general that's Z prime because it's 0. I'm not, the delta function survives only when Z is equal to 0. That is another piece, minus K per square of P of Z comma Z prime is again 0 if I'm in the second region. Again, this is the conductor. This is your Z prime. So that's Z equal to 0. That's Z equal to Z prime. So if Z is here, that's the solution here. If Z is on that side, there is a solution there. But each of this differential equation is solvable. We know the bound solutions to this. This is just harmonic oscillator, right? Or there's a plus sign in here. So each of this equation is of this kind. G is equal to K per square G. And what are the solutions for this? E to the I gives you a minus, right? So it is plus. So G is e raised to plus or minus K per Z. Usually there is an I, but then there are two I's that comes in, makes it a minus. It's just plus or minus. So the general solution of G would be A times e raised to plus K per Z plus B times e raised to minus K per Z. But there are two such solutions. One for this area, one for this area, and then we have to match it. We have to find boundary conditions for it. It's not very obvious how this works, right? So this will be two such solutions, e raised to plus K per Z, d raised to minus K per Z. This is for Z less than Z prime. And this is for greater than Z prime. And we want to match this. So we want to basically find A, B, C, D. And we will have boundary condition. One is that it should be 0 on the surface of the conductor. One is that it should be 0 at infinity. And there are two more conditions we have to search. It's not very obvious what it is. And we want to solve for that. But this is the primary thing. We are looking for solving differential equations like this. Rest everything was formal. This was very generic. If I just Fourier transform it, I get this differential equation. What's the take-home message is that the Fourier modes satisfy one-dimensional differential equation for a conductor that is a simplicity which can be solved. In your homework, this is for a single plate. You do this for 2 plates. And whatever we do on Monday will actually take you very clearly. Thank you. And sorry about the delay today. Hurried
yeah. So why does the Green function not have a K-curve dependence?
It has, right?
No, I mean,
here.
Yeah.
It should. So usually how you write this is the following, right? So it will have. So this is K per. Right? But that is not the primary variable. So you write it as a, it's like a parameter. At this level, this is not a variable, this is a parameter at this differential equation. But when you go back, it is actually a variable. So typically it is written like this. So since I wanted to call that general idea of Green's function, I did not write that. It's almost like saying this has dependence in charge also, right? So, but you don't write it. Like, because you keep that fixed. Right? So at this differential equation, we are talking about a single mode. Right? But there are many modes. For each mode, you add it up. So at that stage, you bring in the K per. So, but it is there, correct? So we'll see that at the end of the solution, we will have K per. It's a good point. Yeah, yeah, it's an important thing. Sorry, I had to hurry a little. So hopefully, it's not too confusing. Okay, thank you. And We didn't have anyone on the other side.